Hello, everybody. My name is Masood Olia, and I'm a professor at School of Engineering at Wentworth University. And I'm here with a problem related to, modeling of, a system, a 2 degree of freedom system, which is related to the topic of vibrations or system dynamics. I would appreciate if you subscribe to my channel and like the video if you indeed like it. And as always, I'll come up with new videos, every week or so. Okay, so what is this problem? So what we have here is a system made of two masses, as you could see, a 2 kilogram mass and a 4 kilogram mass. They are connected to linear springs and a linear damper here. And then we are applying a force, F of t, to it. Now, the objective is eventually get Z1, which is the displacement of mass, mass, the 4 kilogram mass, and Z2, which is the displacement of the 2 kilogram mass, as a function of time. But my goal is not actually to solve this problem analytically, but rather show you how you can get the differential equations and then use the state space actually to indeed simulate this using the Simulink toolbox. So there is a state space block in the Simulink that I will show you shortly. But first we have to get the differential equation. We're going to end up getting two equations, second order equations. So we're going to have second derivatives. And then these two equations are coupled together. So you cannot solve each one independently. Okay, so let me actually turn off my video so I can flatten my device. So just bear with me, guys. Here we go. So I'm going to, this will give me a better position to write things down. So I'm going to start with drawing a free body diagram. So I'm going to start with the free body diagram of a 2 kilogram block. Okay. And then right next to it, I'm going to show you what forces are acting on the 4 kilogram block. Okay. So the first thing that we see is obviously this force. This F of t actually could be anything, could be a function of, a sine wave, a cosine wave, a constant, a ramp function, a step, unit step, or, some other function, and unit impulse, and so on. Now here, in order to get the free body diagram correctly, I'm going to assume that Z2 is greater than Z1. Now you might have a question, why am I using Z instead of X1 and X2? Because you see the notation that we use for a state space, and you'll see it in a minute, is that it will make things confusing. So I'd rather use some other symbol like Z and then leave the X's for the, the state space. So as I said, you'll see what I mean by that. All right, so now look, guys, if you want to find the force that the spring exerts on this 2 kilogram mass right here, that would be the stiffness 8, right? 8 newtons per meter times what? Times the difference of Z2 and Z1, and that was relative displacement. Similarly, you know how the force of damper is. It's the damping coefficient, damping constant 4 Newton seconds per meter times the relative velocity, right? Z dot 2 minus Z dot 1. And then the nice thing is that once you figure out these two forces acting on 2 kilogram block, the forces acting on the 4 kilogram block has to be exactly the same in the opposite direction. And then the force coming from the 6 Newton per meter spring is going to be, since Z1 is moved, the 4 kilogram is moved to the left. So that would be an opposing force of 6 times just Z1. All right. So now we're going to go and apply the equation of motion F equal ma. Keep in mind that you have to pick the direction that are shown here. Like this is the positive direction, and this is the positive direction for Z2 here. Okay, so I'm going to first look at the 4 kilogram mass, and I'm going to pick this direction to be positive. I want to go back actually to black. It's easier to see. So what do we see here? We see two forces that are going in the positive direction. So summing forces and say equal to mass times acceleration. So that's 8 times Z2 minus Z1. And then we have 4 times Z dot 2 minus Z dot 1, right? And then obviously you have the f of t, which would be positive. I'm sorry, I'm looking at the 2 kilogram block. I keep the 4 kilogram block rather, not the 2 kilogram block. So, and then we have a, let's see, a 6Z1, which would be negative, and that's it, equal mass. Mass is 4 kilograms times its acceleration. Acceleration is the second derivative of Z1. So let me come up with the equation, differential equation for the 2 kilogram mass. So for 2 kilogram mass, again, this direction we take as positive, right? What are we going to have? So we see two forces that are going in the negative direction. So minus 8 Z1 minus Z2 minus Z1, right? Minus 4 Z dot 2 minus Z dot 1, right? And then, of course, f of t is going to be positive. We'll see how we handle that within the simulation. And that's equal to mass, which is 2 kilograms times acceleration, which is Z double dot 2. All right. So let's clean this up a little bit. So I'm going to say 4 Z double dot 1. So I'm looking at the first equation. Let's see. How many Z1 do we have? We have a minus 8 Z1 here, a minus 6, minus 14 Z1, plus 8 Z2, and then I'll put the derivatives of minus 4 Z dot 1 and plus 4 Z dot 2. And in a minute, I'm going to actually, normalize this, and I'll tell you what normalization is. Let's look at the second equation. So we have a 2Z dot 2. Again, be consistent. So we put the Z1. So we have a positive 8Z1 and a negative 8Z2 and positive 4Z dot 1 and negative 4Z dot 2. And don't forget the f of t. So now the next step is to normalize this. Normalizing means what? Means, try to isolate the acceleration by itself. So in this case, it means basically divide everything by 4, basically. And in this second equation, divide everything by the coefficient of the, basically divide by mass. So you isolate, or the Z double dot 1 and Z double dot 2. All right, so what happens? We end up getting Z double dot 1 equal, by the way, this is what mistake I made. This is equal and equal. I forgot to put the equal sign here. Sorry, guys. So minus 14 over 4 is minus 3.5 Z1 plus 2Z2, right? Minus Z dot 1 and plus Z dot 2. Second equation, similarly, dividing by 2, we get Z double dot 2 equal 4Z1 minus 4Z2 plus 2Z dot 1, right? Minus 2Z dot 2. And since we're dividing everything by 2, that would be f of t divided by 2. Again, f of t could be anything, some forcing function, right? So now the question is, what do we do with this if we want to simulate this? So of course, you could solve this numerically and get actually Z1 as a function of time, how the 4 kilogram mass is moving, and Z2 as a function of time. But by simulation, we'll see that once we use the state space approach, our goal is to actually get the graphical representation of these two masses, okay? So what we're going to do is, you guys, I have videos actually on the state space, so you can refer to those videos, and shows you more detail of it. So in state space actually is, the format is this: some vector, which represents actually velocity x dot, is equal to some matrix times x as a vector. This x is called the state space vector. And then b times u is actually the input. So u is like f of t here. So obviously these are vectors, and a and b are matrices. And then we have an output vector y, and that would be these guys, z1 and z2, because that's the response to the system, right? We have this matrix C, which is actually called the output matrix, again times x, plus D, which is called the direct transmission matrix, again times U. The key actually, guys, in being able to use Simulink and use this state space block is, in fact, to do the to get these matrices A, B, C, and D, and that's what I want to show you. So actually, what is the idea behind the state space? Basically, a state space is what it does. Any differential equation that you have, and you can have as many as you want, system of differential equation, which is the case here. Remember, this is a 2-degree freedom system, and we'll make it into the first order differential equations, you see, in terms of x dot. And that's why I didn't use x1 and x2. I use z. All right, so how many state space vector do we have? What is x? What do we mean by x? X actually is x1, x2, x3, x4, because for every derivative, so if you have a z1 double dot, we need two state space item, and then the same thing for z double dot 2. So there are 4 of them here, and then how do we set them? So this is the way it's done. So we say, okay, let's say x1, say, is z1, right? And then x2 would be the first derivative of z1, okay? And then x3 becomes z2, and x4 is z dot 2, all right? And this should help us to set it up now. So now we need to go through this, meaning, you know, what is the x dot vector? So actually, I'm going to write it down for you. X dot vector means x dot 1. Actually, before I do that, let me do this. I'll actually go ahead and take the derivative of this. So the derivative of this guy is x dot 1, which is z1 dot. Well, what is z1 dot? Z1 dot is x2. And similarly, x2 dot is what? Is z double dot 1. And what is z double dot 1, guys? It's right here. So that's minus 3.5 z1. What is z1? x1 plus 2z2. What is z2? x3 minus z dot 1. What is z dot 1? x2. See, that's what we're doing. Plus z dot 2, which is x4. You see, now everything in terms of x1, x2, x3, x4. Now, next, the derivative of this guy, x3 dot. What is that? Z dot 2. What is that? Z dot 2 is x4. That. And then finally, x dot 4, which becomes z double dot 2. What is z double dot 2? It's right here, equal to this, right? 4z1. What is 4z1? That's 4x1 minus 4z2. What is that? That is x3 plus 2z dot 1. Z dot 1 is x2, right? And then minus 2 z dot 2, what is that? x4, and then don't forget f of t. Now I'm going to say f of t is u of t, or just u. You don't have to say. So u actually is the input, all right, in this format for the state space. So now look, guys, let me show you how we can get these matrices now. So the first equation, it's really this vector x dot 1, x dot 2, x dot 3, and so on, x dot 4. This is a 4 by 1 vector, obviously. So the question is now, the size of these vectors are very important. See, this is the A vector times what? Times x. What is x? X is x1, x2, I mean, x as a vector, x4, right? So look, guys, in matrices, if this is also 4 by 1, so A then has to be a 4 by 4. So they can set it up now. Look, guys, x dot 1 is what? X2. So that means I'm going to have 0, a 1, a 0, a 0. That's our first equation. Second equation, x dot 2 is what? Let's see, minus 3.5, right? A minus 1 for x2. These are the coefficients. 2 for x3 and a 1 for x4. Just make sure looking at my notes, see everything is in good shape. Yeah, that looks good. All right, x dot 3 is x4. So that's 0, 0, 0, just the 1, right? And then finally, this equation, x dot 4 is 4x1, 2x2, a minus 4x3, and a minus 2. So that's your matrix A. Now, the question is, the only input I have here is f of t, right? So I have just one input. So U is a 1 by 1. The question is, what should be the size of the B matrix here? It has to be a 4 by 1 in order to give me what? An outcome of 4 by 4. These sizes are very important, guys. So let's see. The first equation doesn't have any U, so I have a 0. Second equation, same story, 0. Third equation, same story, 0. But look at the fourth equation. I get a 1/2. 1/2 of U. All right. So now what is the output matrix here? Output really, it's really interesting. Output depends on what you want. Obviously, our goal is to find what? Z1 and Z2. Z1 and Z2 is what? The objective is to find Z1 and Z2. These are the, the position of the two masses, right? The 4 kilogram and the 2 kilogram. So the Y matrix, so it's going to be a 2 by 1 actually. So I'm going to call my Y matrix to be Y1 and Y2. And Y1, let's say Y1 is Z1 and Y2 is Z2, right? So let's go ahead and work this out. So if you want, so this is a 2 by 1 because we decided we just want the displacement. You could also find displacement and velocity. It's possible to do that. So you could get 4 outputs actually. All right. So now, remember, that's equal to what? C, matrix C times X. Remember, X is just a 4 by 1. So this is your X. That is determined from the beginning based on the type of differential equations that we have. So in order to have a 2 by 1, we need a 2 by 4 here. So our matrix B has to be a 2 by 4. So remember now, we want a Z1. So we want Y, Z1. Z1 is what, guys? Let's come back here. Z1 is X1. X1, let me just clean that up for you. X1, so we need a 1, 0, 0, 0. We don't care about X2, X3, X4. And then what is Y2? Y2 is Z2. Z2 is what? Z2 is X3. So then we have a 0, 0, 1, 0. Now, the last thing here in this equation is du. Now, direct transmission matrix for the type of most of the problem that we do is actually a 0 matrix. But the size of it is also important. Remember, U is 1 by 1. We want to have a 2 by 1 outcome, right, on the left-hand side. So this has to be a 2 by 1 then. Remember, this is matrix A so far. This is matrix B. This is matrix C. This one is going to be matrix D, right? So what do I have? Let's see, 0 and 0. So you can actually do a search on the direct transmission matrix. That is when actually in your differential equation, you have the derivative of your u. That's when your d is going to be a non-zero. So at the time, for the time being, you don't have to worry about it. So now the question is, how do you simulate this? That's important. How do we simulate this? So we need to actually input matrix A, B, C, and D. So now let me do this. Let me go to my sorry guys, let me see, where is my MATLAB? Oops. Here we go. All right, so you could actually bring the Simulink by either writing Simulink or just click on the Simulink icon here. All right. And once you get that, right, in MATLAB, you need a blank model. So click on blank model. Once you get your model, go to the library browser right here. Okay. So click on that and you get your library browser, right? And most of the common blocks are here, commonly used block, but I will go, let me see, is the state space here? No. So what I do, I'll go to the continuous block actually. So let's click on continuous. And you see this, the state space is right here. So just drag that and bring it over here. Let me actually enlarge this a little bit for you so you see what's going on. So now we are done with that. Let me actually show you how you can now put the 4 matrices. You see that? That's exactly the form of the state space. So double click on it. And then what you need to do, I got to put my surface in a situation that I could type things. Sorry, guys. So now what I'm going to do, I'm going to, so matrix A was what? Let's go back to our, so matrix A is right here. So what I'm going to do now, I'm going to input that. Now input, you know, just like, let me bring that up. So you would do that like as you writing a, you know, creating matrix in the MATLAB environment. So 0, 1, 0, 0, colon, and a minus 3.5. And this is the second row. Make sure you put 8 spaces, minus 1, 2, 1, colon again. Third row was 0, space 0, 0, 1. And then finally, the last row was 4, 2, -4, and -2. And that's it. That's your matrix A. Now, if there is something wrong, obviously it will prompt you for that. Now, matrix B, if you recall, was a 4 by 1. Here we go, 0, 0, 0, 1/2, right? Right here. Okay, so let's go back to our. So let's see, 0, next row, colon, 0, colon, 0, colon, 0.5, and then close the bracket. That's your matrix B. Matrix C, let me move this around. What was matrix C? It's a 2 by 4, right? You can see in the first row, we have what? 1, 0, 0, 0, colon, and then we have 0, 0, 1, 0. Close the matrix. Now, D is very important, guys. You can't just put 0. The size of it is very important. If you mess up the size, you're going to have an error. So it has to be a 2 by 1, guys, for our problem. So 2 by 1, so 0, colon, and 0. So this should be good. I'll apply this, and I say, okay. Let me go back to my picture here. I mean, my block here. So now what else do I need? Let me bring my library browser. I need actually an input, and then I need an output, which is usually a scope. So inputs are sources. So click on the sources. Actually, I'm going to bring 2 input and try 2 different inputs. So I'm going to bring a constant, and then I'm going to actually bring a sine wave. and I'll run 2 different simulations for you so you can see what's going on. All right, now what is the output? Output is sinks. And that's basically, guys, it's just a scope. All right, so just click on the scope. Let me just go up a little bit here. Where is my, I can't get the scope, so let me search for it. Scope, oh, here we go. So here, the scope, and we are all set. So now we're going to connect these. So this is basically your output. Remember, there are 2 output here, Z1 and Z2, right? And Z1 represents what? The position of mass 1. Let's see, Z1 position of the 4 kilogram mass, and Z2 is position of the 2 kilogram mass, right? Let's go back to our block here. So now let me first do a sine wave for you as an input. So remember, you connect these. I have a video actually on basic, MATLAB and Simulink, so you can refer to that. Let's double click on the sine wave. Let's say we just given some arbitrary amplitude of 1 and some arbitrary frequency, maybe 2 radians per second, and that should do it. Now, let me run this, guys, for maybe, I don't know, 30 seconds. So go here and change that, sorry, 30 seconds. And then you just have to run. Now, if there is any problem, it will prompt you and say there's a problem. Now, hopefully there's no problem. Now, double click on the scope. And look, this is what you're going to get. So the yellow is actually Z1, or the position of mass 1, 4 kilogram mass, and then Z2 is the blue line. Okay, that's how it goes, I think, in the order. All right, so you see 2 outputs here. And because the reason we have something like this is because of the sine wave, guys, as an input, it creates a particular solution which keeps, mimicking that kind of output based on the input. Let me change this now, guys. Let me remove that. And this time I put just a constant here. All right, the constant just means, you're applying a 1 constant force. And let's run it this time, see what happens. And then we double click. Look, this is much nicer. And now with the damper, how come this is not dying down? Because we haven't run it for long enough period. So maybe if I run it for 100 seconds, right? And so I change the stop time. Now I'll double click on the scope to look at the scope. Look, it's dying down. So the amplitude is getting smaller and smaller. Now I have to tell you guys that the nice thing about the state space is that, I'm bringing my picture back. The nice thing about the state space is that you could actually have different outputs. I can have a 4x1 output, and I could have the position of these masses as well as the velocity. Then the size of these matrices are going to change, okay? And you have to input different, matrix C and D. Nothing is going to change, by the way, in the A and B part, but C and D are going to change. And that's what makes the, Simulink and the state space powerful. All right, again, as I said, guys, I have some videos on the state space during the, the time that we were having the problem with COVID, and I was teaching a system dynamics course, electromechanical system for our students. And in that, I showed the detail of, how to set it up. So you can always refer to that if you want. And also some videos I have on basic concepts of, Simulink and, simulating, simple, sine wave or cosine wave and so on. Okay, guys, as always, I appreciate if you subscribe to the channel and like the video. As I said, if you indeed like the video, thank you very much. And I'll see you guys soon.